So, hi, good morning to all. I'm Dr. Neeti. I'll be presenting the next talk. Right. At the outset, I'd like to thank the organizers and especially Dr. Bindu for giving me the opportunity to present today's this talk. Let's move on to what we'll be discussing today. Right. So the topic that will be discussed today is, by me is sleep wakefulness behavior in animal model and the efficacy of circadian manipulation in an animal model of neuropsychiatric disorder. So the outline for the talk is that we briefly get into the introduction of the topics that is to be discussed, and we'll look into sleep wakefulness behavior in animal model, and also discuss efficacy of non-pharmacological intervention, such as circadian manipulation in the recovery of sleep disturbances in animal model of a neuropsychiatric disorder. Right. So any rhythm which is about 24 hours is termed as circadian rhythm. Circadian in Latin circa diem means about a day, which is about 24 hours here on Earth. In mammals, suprachiasmatic nuclei or SCN, which is present in the anterior hypothalamus, generates and maintains this 24-hour rhythm with the help of a molecular mechanism, molecular machinery. This biological clock is endogenous and it's maintained without any external input. There are other tissues and organs which also generate this 24-hour rhythm independent of SCN. SCN in turn regulates most, if not all, 24-hour rhythms, which includes behavioral, physiological, biochemical rhythms, right? So one of the downstream rhythms, which is of particular importance in this talk, is maintenance of sleep-wake cycle, right? So the suprachiasmatic nuclei is an endogenous biological clock, which maintains downstream 24-hour rhythm, such as sleep-wake cycle, cognitive performance, etc. It also regulates other tissues that I was talking about in this 24-hour rhythm, and also peripheral outputs to bring about physiology and behavior. So what happens to this endogenous system when subjected to external cues? One of the strongest cue to which this endogenous clock is subjected to is light, which is also known as these external cues which regulate the endogenous clock, also called Zeitgebers in German for time giver. Right. So we'll look at what one of the experiments. We'll look at what happens in the presence of light. What happens to the free running period of sleep-wake cycle, right? The other cues which also influence this endogenous clock is feeding schedules and activity. And today we'll especially be talking about sleep-wake cycle modulated by circadian rhythm. So SCN, which generates this rhythm, runs in it's an endogenous system, rhythm system, which in the absence of light-dark cycle also produces sleep-wake cycles. So this figure here represents sleep. The dark region represents the activity of the animal, and the blank region represents the sleep schedule. And this is plotted for 24 hours and double plotted for, to see the continuity of the activity or sleep events. So the first line represents the first day's activity and sleep, followed by the following second day's activity and sleep, so that we see a continuity of activity to better interpretation of this kind of study. So the animal was subjected to or maintained in constant darkness, and the sleep and wake activity were observed. So in a free running period, in the absence of external environmental cues, the animal still maintains activity and sleep, right? Except this endogenous clock is a little longer than the 24 hours that is observed in a circadian rhythm. So what happens to the system when subjected to a light-dark schedule of 12 and 12 is that it synchronizes the activity at light on, especially because this study was done in a diurnal animal, which is active during the day and sleeps during the night, is it synchronizes the activity at light on and goes on to continue the sleep and becomes active when the light is on again and goes on to sleep. So when the animal is presented with an external cue such as light, which is a very strong Zeitgeber or environmental cue, the sleep-wake cycle becomes entrained to the external cue. And this is very important because most of our activity also has been evolved and adapted to this light-dark schedule that we see because of the because the Earth moves around the sun, and there's a 12-hour light-dark schedule, right? So the circadian and sleep centers have evolved together to ensure the timing of internal events relative to one another, which are endogenous, and to the external environment is coordinated in such a fashion to maximize the survival of the species. So I'll be repeating when I talk about the introduction to sleep, because you've already heard it multiple times in different talks yesterday. Sleep can be defined as a reversible behavioral state of a perceptual disengagement from and unresponsive to environment. And it has been highly conserved phenomenon across animal kingdom, right? So especially because it is involved in several functions, which include energy conservation, restoration and recovery, memory functions, brain development, brain and body homeostasis, health and survival, and adaptation to external environment. So what happens when this rhythm is disturbed? Or the other way around is when sleep and circadian systems are reported as a comorbidities in patients with psychiatric disorders or neurodegenerative diseases. So some of the ones that I discussed here are what happens in depression. Depression delays sleep-wake schedule is observed, short latency to REM sleep, increased REM density and increased REM sleep is observed. In Alzheimer's disease, shortened sleep duration, low sleep frequency, quality, excessive daytime sleepiness, long sleep latencies also are reported. In Parkinson's, insomnia, daytime sleepiness, parasomnia, and restless leg syndrome have also been reported. So it's important to study. So we don't know, we are not clear about the etiology of these disturbances of sleep and circadian rhythm observed in these neuropsychiatric disorders. So it's important to study these disorders in animal models to figure out, to elucidate what is the underlying mechanisms, right? Before going into one of the models that has been been used in our lab to study the underlying mechanisms of neurodegenerative and psychiatric disorder, I'll be talking about how sleep in animal models and the sleep scoring, especially in rodent model. And then we'll move on to the sleep characteristics in this model that has been used in our lab. So the sleep wakefulness has been demonstrated all the way from the lower phylum to higher mammals. Sleep is also studied in jellyfish. So in lower organisms, unlike in mammals, which has the sleep is divided into different stages of non-REM sleep and REM sleep with wakefulness. In lower organisms, it's basically whether they're at rest in quiescent stage or whether they're active. So in jellyfish, it is imaged in a microscopic setup where the change in pixel is quantified and mapped. It is shown that during daytime, the activity of the animal is more as compared to when the jellyfish was observed during night. Sleep is also studied in reptiles, where it shows characteristic feature of non-REM sleep of high amplitude, low frequency, and low frequency and a high amplitude rhythm in electrophysiological recording oscillations, right? So in birds also, different stages have been demonstrated, where the blue is active, the wake stage, and red represents non-REM stage, and green REM stage. So we look into how sleep is studied in rat. Like in humans, we implant electroencephalographic electrodes and EMG electrodes and electromyographic and electrooculogram electrodes in rats also. So in rats, we do it is an invasive procedure, and we do implantation under anesthesia. For a cortical and EEG, we implant 2 electrodes in frontal cortex. We also have a depth electrode in hippocampus, and bilateral EMG electrodes and EOG electrodes. EMG is implanted in nuchal muscles, and EOG implanted in external canthal muscle around the eye. So we give post-surgical, we give about 7 to 10 days for post-surgical recovery. Once the animal has recovered, we connect the animal to the system with a flexible wire, which is connected to the implant, and the other end is connected to the amplifier. The animal, along with EEG recording, is being video monitored constantly, so that if there's any discrepancy, we can, in the absence, or if we find something, some artifacts, we need to confirm that during the scoring procedure. Right, so we use an IR camera. So in the absence of complete light, when the animal is maintained in darkness, we are able to observe the behavior. So as mentioned earlier, in animals, in rodents also, we use EEG, EMG, and EOG electrodes to record polysomnography. Okay, so what does the different stages look like in animals, right? So it is divided into in wake, non-REM, non-rapid eye movement stage, and rapid eye movement stage. Wake further is divided in rodents as active wake and quiet wake. Active wake is when the animal is actively moving around in the chamber that I just showed. And this is how the EEG looks like. It has low amplitude, high frequency. This image is for a 10-second epoch. And we do recording. We study the sleep-wake behavior for 24 hours. Or rather, we have studied for 24 hours. And the sleep-wake behavior is scored for every 10-second epoch. So this image gives a snapshot of a 10-second epoch. EEG in ECOG is the EEG for cortical electrode from the screw electrode. Shows low amplitude, high frequency oscillations. In CA1 region of hippocampus shows theta rhythm. EMG shows movement artifact, depicting high activity, and EOG also shows movement, high activity due to eye movements. So the other stage in wake is quiet wake, when the animal is stationary and sitting in one position. The cortical EEG remains the same. There is no noticeable difference with active wake, except the active theta rhythm is not observed during quiet wake. The EMG activity has considerably reduced, and no movement artifacts is observed. EOG shows reduced activity with occasional eyeball movement. In non-REM sleep, in rats is further divided into S1, S and S2 stage. S1 stage is primarily detected with the help of spindles present in the epoch, and it also shows high amplitude and low frequency EEG. Same with the depth electrode or in hippocampus. EMG and EOG, we see considerable reduction in activity in the absence of locomotor activity. The rat also shows a very typical behavioral body posture during different stages of sleep. In non-REM S1 stage, slow wave sleep stage, the animal is either stretched, it sleeps in a stretched position. When it moves on to non-REM or S2 stage, the cortical activity, we see delta range oscillations with high amplitude and 0.5 to 4 Hertz frequency. It's similar with EEG in hippocampus. And EMG shows it's comparably reduced when in comparison to N1 stage, and eye movement were also absent. In transition stage from non-REM to REM, we see a mixed wave pattern of theta and delta waves, high amplitude low frequency and low frequency high amplitude waves. EMG also is considerably low, and EOG signal movement signal is considerably low even in EOG and EMG, right? So in rapid eye movement or paradoxical sleep stage, we see high frequency, low amplitude waves in cortical EEG, and we also observe theta frequency, theta REM theta in hippocampal depth electrode. Muscle electrodes, EMG electrodes show muscle atonia, and EOG electrodes show rapid eye movement. And it also shows a very characteristic curled up position in REM sleep. Okay, so it is recommended to observe the animal's behavior during scoring, because one of the things that we realize and often not reported, or probably it's in common knowledge, is the fact that rats sleep with the eyes open during non-REM sleep, which where the EEG shows a characteristic of a non-REM, but the rats are with eyes open. So there was a confusion as to which stage do we score this epoch to. And then when we went back and looked at literature, it actually, there are reports where they say that rats indeed sleep with eyes open some part of the night. And this phenomenon is more when the animal is sleep deprived or subjected to stress protocols. So we constantly observe the video along with the scoring, the EEG characteristic while scoring for animal EEG. So these are the different stages in light and dark period, representative images for different stages. So there's an option, depending on your study protocol, you will decide whether you want to study each of these stages and quantify them separately, or club them into what has been represented here, where wake and active are clubbed together and scored as wake stage. Non-REM stage, S1, S2, and transition stage are combined together and scored as non-REM stage. And of course, you have the REM stage separately. So this is a representative image of light and dark phase sleep scoring, and this is the hypnogram for 24 hours, where the rats have been maintained in 12-hour light and dark phase, dark period. So having gone through or presented the how sleep is studied in rodents. We will move on to the model where we use a non-pharmacological intervention to observe sleep disturbances in the animal model of neuropsychiatric disorder. So earlier studies in the lab with this rat model, wherein we lesion particular region of hippocampus, and we have studied cognitive and other parameters. We observed that rats with the ventral subicular lesion showed considerable cognitive deficits in forearm and radial arm weighted tasks. They also showed deficit in water maze tasks, depicting that this region was involved in spatial learning and cognition. Further, on morphological assessments, they also showed degeneration in dendritic branching and in spine density, especially in CA1, CA3 region of hippocampus and internuclear cortex. Subiculum has been implicated in early progression of Alzheimer's disease, and plaques have been observed in subiculum and temporal cortex, and later on also in other hippocampal structures. Atrophy in pre-subiculum and subiculum is considered as a earliest hippocampal anatomical marker for AD. Many individuals suffering from AD, dementia, delirium, and Parkinson's disease exhibit sundown phenomenon. So it is a set of characteristic features in which includes agitation, confusion, mood swings, and anxiety-like behavior, anxiety behavior that appears only during later part of the day, mostly during sunset. So the cause behind this phenomenon is not very well understood, and it is possible, and we hypothesize that it is possible that it's because of disruption in circadian rhythm. Right. So with the model which shows neurodegeneration, which resembles AD, we recent studies, we further moved on to look into anxiety and depression-like behavior to see how ventral subiculum lesion in rats to see this behavior in ventral subicular lesion rats, right? So recent studies we have with VSL model, we have seen anxiety and depression-like behavior. And along with this, we also assessed efficacy of non-pharmacological intervention, like I said, with the circadian rhythm manipulation. Especially, we used manipulation of photoperiod light to see the effect on these behaviors. So it was shown, so the behavior were assessed using open field, elevated plus maze for anxiety-like behavior, and splash test and sucrose preference test, and forced swim test for depression-like behavior. So normal rats were maintained in 12-hour light period, while animals which are subjected to short photoperiod were maintained in 6 hours light and 18 hours darkness. So different groups that were used for were normal control, vehicle control, and ventral subicular rats. Normal control rats did not undergo any intervention. Vehicle control rats had infusion of phosphate buffer saline into ventral subiculum, and ibotenic acid was used for lesion ventral subiculum. So following 7 days of recovery and 21 days of exposure to either normal photoperiod or short photoperiod, these behaviors were assessed. Ventral subicular rats showed the anxiety-like behavior is demonstrated in open field by reduction in exploration to the center, and most time is spent in the periphery. The anxiety phenotype in elevated plus is that the elevated plus maze has 2 arms, which is open and another is closed. More anxious animals tend not to explore the open arms and remain in the closed arms. So the VSL rats showed decreased time spent in the center and more time spent in periphery. While exposure to short photoperiod, this behavior was reduced. So they explored more in the center and less in the periphery. Similarly, time spent in open arm was considerably reduced, significantly reduced in VSL rats, which was in the anxiety-like behavior was improved when subjected to SPR. There were more time spent in open arms. Entries were more in open arm in elevated plasmas. So when we studied, so splash test is used to assess grooming behavior and motivation. Sucrose preference test is a test used for demonstrating pleasure-like behavior. And force swim test is used for behavioral despair, which are the measures for depression-like behavior in animals. BSL rat showed considerable decrease in significant decrease in grooming behavior as latency to groom was high, and it was improved with exposure to SPR. Similarly, sucrose preference test also, the animal prefers, when presented with the choice of water and sucrose, it preferred, the VSL animal preferred less, showed less preference to sucrose consumption, sucrose water consumption as opposed to water, but it was improved with exposure to SPR. In force swim test, VSL rat showed longer time being immobile, and it was improved with exposure to SPR. And we also looked into levels of corticosterone, plasma corticosterone in different groups. And it was observed that it was elevated in VSL rats and was reduced following exposure to SPR. So these observations encourage us to undertake sleep-wake behavior in VSL rats to assess the impact of ventral cervical lesion on sleep-wake behavior. And we also wanted to study what is the effect of short photoperiod manipulation on these rats subjected to ventral cervical lesioning. Right, so study design goes this way. We acquired about 2.5 to 3 months old rats, and the animals were subjected to surgical intervention where when ibotenic acid was used to lesion ventral cerviculum, and following which we implanted electrodes for assessment of sleep-wake behavior. 7 days of post-surgical recovery time was given, following which we acquired baseline sleep-wake recording. And the animals from vehicle control and VSL were either subjected to normal photoperiod or short photoperiod for a period of 21 days. And post-exposure to either one of photoperiod normal and photoperiod manipulation, post-exposure sleep-wake behavior recording was acquired. The animal, as I showed you earlier in the video, the animal was connected to the system using a connector, which is connected to the head stage, and the other end connected to the amp. A swivel or a commutator, which allows the animal to move around freely without any inhibition or restriction. So the EEG signals were acquired using BESS acquisition system, and this is a representative figure of the EEG recording. So here are the results for the effect of subicular lesioning on sleep wakefulness behavior. Following, this is a baseline data. Following 7 days of post-surgical recovery, and the animals were connected to the system, and sleep scoring was performed and taken as baseline data. It showed, when compared to control, the animals showed the ventral cervical lesion animals showed enhanced total sleep, non-REM sleep as well as REM sleep. And this change was primarily restricted to the light period of the day. And all these animals were maintained in normal photoperiod, 12-hour light and 12-hour darkness. This graph shows a distribution of sleep non-REM and REM across one hour bins. Although we didn't see a significant change between the groups across time, there was a total difference of sleep, non-REM and REM sleep. So this data shows what happens to sleep-wake behavior following exposure to SPR. The same animals which were subjected to baseline recording were subjected to different both NPR and SPR photoperiod, and we observed that in BSL rats which were continued to be maintained in NPR, they showed enhanced sleep, while when subjected to SPR, the total sleep duration had reduced, and this was primarily the reduction was primarily seen in non-REM sleep, and the animals. Yeah, so primarily in non-REM sleep, and there was no change in REM sleep. So this is a representative image of 1 hour bin for sleep time, non-REM and REM sleep. So this graph represents the white and dark bars represent 12-hour light schedule for normal photoperiod, and the white and gray background show light and dark period for data for animals subjected to short photoperiod. So what we observed is there was as soon as the light was off for short photoperiod, there's an increase in activity of the animal, which was seen, continue to be seen in dark phase, and the next 12 hours was common between both NPR and SPR. So the decrease was seen predominantly in the first 6 hours of dark phase in short photoperiod regime. So this can be appreciated in this graph, where we showed that in light phase, the BSL animal still continues to have enhanced sleep, while in short photoperiod, both both BC and BSL showed decrease in sleep and non-REM sleep in the first 6 hours, that is from circadian time 6 to 12 in sleep as well as in non-REM sleep. So whatever change that was observed is primarily in this region, where increase in short photoperiod led to increased activity in these animals. So to conclude, to summarize the effect of VSL on sleep wakefulness behavior, the reason why there was enhanced sleep observed in these ventral subicular lesion rat could be because ventral subiculum has direct connections with the suprachiasmatic nucleus, and which is involved in circadian rhythm regulation, and also to VLPO, which is another critical region implicated, or sleep promoting region in mammals. The lesion would have also affected sleep homeostasis in terms of the lesion affected sleep duration, implicating role of ventral subiculum in sleep-wake regulation. Further increase in sleep following BSL could also have been as a result of stress response. As earlier, as I showed the data, the BSL animals showed enhanced corticosterone, plasma corticosterone level, and it is also for the fact that BSL plays a major role in stress integration and regulation of HPA axis. And disinhibition and lesioning, and thus the disinhibition of ventral subiculum could have increased the hormone levels and caused the stress-like phenotype. Enhanced sleep and consistent increase in delta power during non-REM sleep, and with the heavy fragmentation and reduced maintenance of wakefulness, and frequent interruption in REM sleep are also observed in animals with high anxiety. Right. So non-REM and REM sleep rebound observed in this study could be an adaptive mechanism to stress and anxiety-like phenotype. So the effect of sleep wakefulness behavior in VSL, although both VC and VSL showed response to short photoperiod, VSL exposure facilitated restoration of sleep wakefulness behavior in VSL following SPR exposure. As we observed a decrease in total sleep time, predominantly in non-REM sleep. However, what we observed in VSL rat showed a phasic pattern of sharp peaks and sleep alternating with wakefulness across dark period. So the effect of exposure to short photoperiod appears to be need-based, and it has beneficial outcome in VSL rats, and thus helps in restoration of sleep wakefulness behavior. This recovery may be correlated with amelioration of anxiety and depressive-like behavior in VSL rats, as seen in the behavioral studies. Moreover, modulation of sleep-wake pattern in VSL rat may also have contributed to the behavioral recovery. On the other hand, the control rat showed disturbed circadian rhythmicity on exposure to short photoperiod. Although sleep homeostasis was not affected, the total sleep time remained safe, except the pattern of sleep was affected. So exposure to short photoperiod mediated attenuation of enhanced sleep and augmentation of activity in VSL rats, and that could have helped in recovery. So studies such as this may allow comprehensive understanding of mechanisms involved in sleep disturbances and behavioral recovery in mood disorders by photoperiod manipulation, and to design interventions appropriately to observe the efficacy. So, thank you.